Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us to the edge of what we think we know, to a place where the shadows of black holes might be hiding something else entirely. We will wander together into the idea of gravastars, objects that look like black holes, wear their dark clothes, cast their familiar shadows, and yet keep a secret inside that changes the story. But before you settle in and get cozy, I'd love it if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into gravastars together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. We'll begin not with equations or diagrams, but with an image, a patch of sky so still, so dark that it seems almost empty. And then, at the centre of that darkness, something is bending the light of distant stars. It is invisible itself, yet the curve it leaves in the fabric of space tells us it is there. Astronomers might look at such a place and say there's a black hole, and perhaps they are right. But perhaps they are only half right. For decades, black holes have been the ruling monarchs of the invisible kingdom. They are the end point of massive stars, the final act of gravity's relentless pull. They have been in our textbooks, in our science fiction, and in our imaginations, the perfect symbols of mystery. But sometimes, the things we take for granted are the very things worth looking at again. Imagine, for a moment, a door you've walked past your whole life, certain you know what's behind it. And one day someone whispers, "What if it's not what you think?" Gravastars are that whisper. The name is short for gravitational vacuum star, but don't let the formality put you off. The idea is simple enough to picture. A gravastar would be an object just as massive and compact as a black hole, but instead of a singularity hidden behind an event horizon, it has a different heart entirely. A bubble of something like dark energy at its core, wrapped in a thin, dense shell of exotic matter. From the outside, it would look exactly like a black hole. Its gravity would bend light in the same way. Its shadow would seem just as inescapable. But inside, the story changes completely. We will have time in later moments to open that story carefully, to see what is inside and why it might exist at all. But here, at the very start, I want you to simply hold the image of two things that look the same but are not the same, like twins who share a face but not a life. If gravastars are real, they would be the perfect cosmic imposters. We could be looking at them already, mistaking them for black holes in photographs from the Event Horizon Telescope, or in the ripples detected by LIGO after colossal collisions. The difference between them and black holes would be hidden not in the way they appear at a glance, but in the way they behave deep down, in moments so subtle that our instruments are only now beginning to have the patience to notice. Part of what makes this idea so fascinating and so quietly unsettling is that it challenges a story we thought was finished. We had accepted that when a massive star dies, it either scatters itself in a supernova, leaving behind a neutron star, or collapses so completely that it becomes a black hole. That was the clean ending. But gravastars ask us to imagine another path, one where the collapse halts just before the point of no return, where something in the very fabric of space pushes back, holding the core open, resisting the ultimate fall. It's like watching a candle go out, only for the flame to flicker back into life in another colour, or standing by a frozen lake, thinking it is solid to the bottom, and discovering there is a warm pocket beneath the ice. Gravastars would be that warm pocket, hidden beneath the frozen shell of what we thought was a dead star. Of course, ideas like this don't arrive in the middle of a perfectly calm sea. They tend to appear when the waters are already troubled, And in physics, those troubled waters have long been stirred by the problems with black holes. Singularities, those infinitely dense points predicted by Einstein's equations, are uncomfortable guests in our theories. And event horizons, those one-way doors, make information vanish in ways that seem to clash with the rules of quantum mechanics. Mazur and Mottola, the two scientists who first put Gravastars into words, weren't trying to be dramatic. They were simply asking, what if we can keep all the good parts of black holes, their gravity, their elegance, but avoid the infinities and paradoxes that make them such awkward companions to the rest of physics? Their answer was a kind of cosmic compromise. Replace the singularity with a smooth bubble of vacuum energy. Replace the event horizon with a thin but impenetrable shell, and let the rest of the universe see only the same dark silhouette it always has. We will explore how such a thing might form, what clues it might leave, and why some scientists believe they might already be out there. But for now, it is enough to feel the weight of the idea that in the vastness above us there could be shadows we think we know, that are in fact something else entirely, and that sometimes the universe still keeps secrets not by hiding them from our eyes, but by letting them look exactly like the things we already trust. So let's take our first step. The knock is at the door. The light outside is bending, and perhaps when we open it, it will not be a black hole that greets us, but something wearing its clothes, waiting patiently to be noticed. When you picture a scientific discovery, you might imagine bright laboratories, the hum of machines, white coats, and bustling teams rushing to uncover the next great truth. But in reality, some of the most intriguing ideas are born quietly, without fanfare, in the minds of just a few people who are willing to question what most of us have already accepted. It was the early 2000s, and in the world of astrophysics, black holes were not a topic of debate. They were a given, an unavoidable conclusion of Einstein's general relativity and decades of indirect evidence. We had not yet taken a photograph of one, but the math was clean, the theory was compelling, and the universe seemed to agree. If something had enough mass and collapsed past a certain point, it became a black hole. That was simply the end of the story. But end-of-story moments in science can be deceptive. They are rarely as final as they appear. Somewhere in the back rooms of thought, a quiet restlessness can stir, a sense that the picture is almost right, but not quite. And for two physicists, Pavlo Mazur and Emil Mottola, that restlessness had been growing. Mazur and Mottola were not trying to tear down the concept of black holes. They admired their elegance, their inevitability, but they were also aware of the discomfort black holes caused when placed alongside quantum mechanics, the other great pillar of modern physics. In quantum theory, information cannot be destroyed. In a black hole, as far as we can tell, it is swallowed whole, never to return. This was not the only problem. At the very heart of a black hole, general relativity predicts a singularity, a point of infinite density, infinite curvature of space and time. Infinities like that are not so much answers as they are signs that the math has reached its limits, that it is pointing beyond itself. Physicists, like careful travellers, take such signs seriously. A singularity is a place where the road ends, where the familiar laws of nature fall silent. Mazur and Mottola began to ask, what if the road doesn't end? What if, at the point where gravity seems unstoppable, something changes? Not a violent change, but a quiet one. The kind of shift you might not notice at first, like a subtle change in the air before rain. Their proposal was simple in concept, though rich in detail. Imagine the collapse of a massive star. As gravity tightens its grip, the matter inside is crushed closer and closer together. In the standard picture, nothing can stop it once it passes a certain threshold. But Mazur and Mottola suggested that, under the extreme conditions near that threshold, space-time itself could undergo a kind of phase change, like water turning into ice, or steam condensing into water. In their model, The core of the collapsing star doesn't continue into a singularity. Instead, it becomes a bubble of vacuum energy, a region where the pressure is negative, pushing outward, resisting further collapse. This is the same kind of energy thought to drive the expansion of the universe on the larger scales, but here it would be trapped inside a star's remains, holding them apart from within. Around that core would be a thin shell of ultra-dense matter, not quite the matter we are familiar with, but something stiffer, stranger, and capable of withstanding unimaginable forces. This shell would sit exactly where the event horizon of a black hole would be, giving the object the same outer appearance. From the outside, all the familiar signatures of a black hole would still be there. The intense gravitational pull, the bending of light, the shadow in the centre of an accretion disk. But just beyond that shadow would be a surface, a place wherein falling matter would crash and radiate energy instead of vanishing into the abyss. This was the Gravastar, the gravitational vacuum star, a name that sounded technical, but which hinted at something poetic, a star that had traded the usual burning of nuclear fuel for the silent pressure of empty space. To many in the physics community, it was an interesting but speculative idea. Black holes were already well established in theory and observation, even if not yet imaged directly. Replacing them with something unproven seemed, at best, unnecessary. But Mazur and Motola's work was not about replacing. It was about widening the frame, allowing for the possibility that nature had more than one way of making a dark, compact object. If you think of science as a grand cathedral, black holes were one of its towering spires, elegant, iconic, and firmly set in place. Gravastars were like a hidden stairway inside that spire, leading to a room most visitors never knew was there. You could walk past the building every day and never suspect it was inside, but once you learned it existed, you might start to wonder how many other rooms you hadn't yet seen. In the years since their paper, the idea of Gravastars has lingered on the edges of astrophysical discussions. It hasn't taken the spotlight, but it hasn't vanished either. New advances, gravitational wave detectors like LIGO, the Event Horizon Telescope's shadow images, have given us tools that could, in theory, reveal differences between black holes and Gravastars. So far, nothing has ruled Gravastars out. Mazur and Motola's lamp in the dark was not a blinding light. It was a small, steady flame, enough to illuminate a possibility and invite others to look closer. And perhaps that is how many of the universe's deeper truths first arrive, not with the certainty of daylight, but with the patient glow of an idea willing to wait. As we continue, we'll step closer to the heart of the problem that Gravastars were designed to address. We'll see why black holes, for all their power and mystery, have been troublesome guests in our physics, and why replacing their most extreme features with something gentler might help us sleep a little easier under the stars. If you've ever sliced into a cake, or peeled an orange, or even cracked open a seashell, you know that the outer surface rarely tells the whole story. The outside is what the world sees, the rind, the frosting, the polished shell. But the inside can be something altogether different, layered and unexpected. Gravastars, if they exist, would be built the same way. From a distance, you wouldn't see those layers at all. All you'd notice is the shadow they cast, a perfectly round absence in the light, a gravity so strong that even starlight bends around it in graceful arcs. It would be indistinguishable from a black hole in almost every way we can measure with today's telescopes. But if you could peel it open, carefully, as if unwrapping something fragile and ancient, you would find not a bottomless pit, but a structure as deliberate as a crafted object. At the very heart of this structure is the core, a bubble of what physicists call vacuum energy, though the name doesn't quite do justice to what it is. In everyday language, vacuum means empty, like an unused room or an unfilled jar, but in physics, a vacuum can be anything but empty. It can be a restless nothingness, a background sea of energy that exerts pressure on space itself. In a Gravastars case, the pressure is negative, meaning it pushes outward as if the heart of the star were breathing gently against the pull of gravity. You might think of it like a balloon. Air inside a balloon presses outwards, keeping the rubber stretched. In a Gravastar, the vacuum energy inside the core plays the same role, holding the inner walls apart. This outward push is not a violent explosion, but a steady resistance, the kind that holds a structure in delicate balance for as long as conditions remain unchanged. Surrounding this core is the shell, thin in scale but unimaginably dense and stiff. It's not made of the kind of matter that forms planets or people. This is exotic matter, with properties that may not exist anywhere else in the universe, except under such extreme conditions. It would have to be strong enough to withstand the core's outward push and the universe's inward pull at the same time, like a bridge suspended between two opposing forces. Physicists sometimes describe it as ultra-stiff matter, which isn't a phrase that brings much comfort but does tell you something about its resilience. This shell would sit at a radius almost exactly where the event horizon of a black hole would be. That's why, from the outside, it's so hard to tell the difference. Any light trying to skim past would still be bent nearly as much as it would be around a black hole, and anything falling toward it would accelerate in almost the same way. If you could hover above it, which is already impossible with our current technology, but let's imagine, you wouldn't see a visible surface. The shell would be cloaked in the extreme warping of space-time. To any observer far away, it would be buried in the same deep gravitational shadow as a black hole's edge. And beyond that shell, there's nothing particularly special in the conventional sense, just empty space extending outward to the rest of the universe. The exterior gravitational field would match that of a black hole of the same mass. To the laws of general relativity, both would be identical from the outside in terms of how they bend space. That's why Gravastars can hide in plain sight. They mimic all the big, obvious signatures. The differences begin only when you imagine crossing that invisible boundary. In a black hole, passing the event horizon means there is no coming back. There is no surface to stand on, no solid ground, just a one-way descent toward the singularity. In a Gravastar, there is a surface, unimaginably hot, incredibly dense, and utterly unwelcoming, but a surface nonetheless. Matter falling onto it would smash against that shell, releasing its energy in a final, spectacular flare. This is more than just a detail. That shell, and the core it protects, solve problems that have been nagging physicists for decades. In a black hole, information about whatever falls in is believed to be lost forever, a fact that doesn't sit well with quantum mechanics. In a Gravastar, that information could be stored in the shell, preserved in some encoded form, or slowly released back into space. The infinite density of a singularity is replaced by the finite pressure of exotic matter. The one-way trap of an event horizon is replaced by a barrier that reflects, absorbs, and responds. It's worth pausing here to think about how unusual that is in cosmic terms. The universe, for all its variety, is surprisingly repetitive in its designs. Stars are born from clouds of gas, live by fusing hydrogen, and die according to their mass. Planets form from disks of dust, solidifying into spheres. The rules are consistent, the outcomes predictable. Gravastars, if they are real, would be one of those rare cases where the universe finds a loophole, a way to arrive at the same outward appearance by travelling a completely different path inside. Perhaps this is why the Gravastar idea feels both unsettling and strangely comforting. Unsettling because it suggests that some of the most extreme objects in the universe are not what we think. Comforting because it means there might be ways for the cosmos to avoid the sharp edges we have imagined, the infinities, the absolute endings. It's as though the universe has built a softer interior beneath a hard mask, as if to say, the story goes on, even here. In the sessions ahead, we'll see why such a layered design might have been necessary in the first place, why physicists like Mazur and Mottola felt that the black hole story needed revisiting. For now, Just hold that image in your mind. A sphere in space, dark as a black hole, but within it, 3 quiet layers, a gentle push at the centre, a wall of unimaginable strength, and an exterior that hides them both perfectly from view. If you've ever dropped something fragile and watched it shatter, you know the feeling of a moment suddenly reduced to fragments. Now imagine that instead of fragments, all the pieces kept falling inward, collapsing into a smaller and smaller space until there was no space left at all. That's the picture general relativity paints for the core of a black hole, a singularity. It's a word that sounds mysterious, but in physics it has a very specific and slightly unsettling meaning. A singularity is a place where the numbers we use to describe the universe stop behaving. Distances shrink to zero, density climbs to infinity, and time itself seems to lose all meaning. It's not just that we don't know what happens there, it's that the very framework we use to know things breaks apart. Physicists have a kind of instinctive caution around infinities. In mathematics, they can be useful as limits or abstract concepts. But in physics, the attempt to describe a real physical universe, infinities are usually a warning sign. They're like the danger symbol on a map telling you you've reached a place where your tools no longer work. In the case of a black hole, the singularity is predicted to sit at the very centre, hidden away behind the event horizon. No light can escape to tell us what's there. No signal can report back. In that sense, it's a mystery not just in practice but in principle, one we might never see directly. And yet, the idea that there is an actual point of infinite density inside the universe is difficult to swallow. Physics has often encountered infinities before, only to resolve them with a deeper understanding. The electric field around an electron, for example, once seemed infinite at zero distance, until quantum theory stepped in with a better description. The same has happened in thermodynamics, in particle physics, in many corners of science where infinities appeared. Almost always, the infinity was a sign that the theory was incomplete, that a more careful picture would smooth the spike into something finite and well-behaved. This is why singularities make physicists uneasy. They're not just mysterious, they're suspicious. They hint that we've pushed Einstein's equations beyond the place they were meant to go, into territory where quantum mechanics should have a say. General relativity is magnificent at describing the large-scale structure of space and time, but quantum theory rules the small, the chaotic, the probabilistic. In a singularity, those two regimes collide, and instead of giving us a neat answer, they give us an unresolved conflict. Quantum theory, in particular, resists the idea of a singularity because it doesn't like infinities in the fabric of reality. In quantum mechanics, even the vacuum, what we might think of as empty space, has a structure, a set of fluctuating fields and probabilities. It's never just nothing. So the idea that matter could be crushed into a point where space itself is undefined goes against that grain. To quantum theory, the singularity is not a final destination but a flashing sign that says, you need a new theory here. Some physicists suspect that when we finally unite quantum mechanics and gravity into a single framework, something like a theory of quantum gravity, the singularity will vanish from the equations. In its place might be a region of extreme but finite density, or a bounce, or a phase of space-time we haven't imagined yet. This is where ideas like Gravastars begin to sound appealing. They replace the singularity with something smoother, something that plays better with both sets of laws. It's a bit like walking into a room where two musicians are playing different tunes. At first the sounds clash, notes colliding, rhythms fighting each other. The singularity is the moment where that clash reaches its loudest, most unbearable point. A Gravastar, or another quantum gravity object, would be like changing the arrangement so that both melodies flow together, not perfectly, but without tearing the music apart. And maybe that's why this heart of nothingness bothers us so much. We can imagine an absence, a space where there is nothing. But a singularity isn't just absence. It's an end to the very stage on which the universe plays. It's not the lights going out. It's the theatre itself disappearing, the floorboards collapsing into a point, the air vanishing between your hands. Gravastars, as we'll see, offer a different ending to that play. They keep the walls standing, the floor in place, and replace the void with something that pushes gently outward, instead of crushing inward without end. They may not be the final answer, but they are a reminder that infinities are often invitations to look closer, to think differently, to believe the universe might have chosen a subtler path than the one our first equations gave us. Imagine standing in front of an old, heavy door in a forgotten part of a building. Its hinges are rusted, its wood darkened by age. You reach for the handle, curious, and push. It opens easily enough, but when you try to pull it back toward you, it will not move. The latch is gone, the handle is only decoration, and the door was never meant to be opened from this side. Once you step through, there is no returning. In the language of physics, that one-way door is called an event horizon. It is the invisible boundary around a black hole, where the pull of gravity becomes so absolute that not even light, the fastest traveller in the universe, can escape. The name event horizon is precise in its poetry. Anything that happens beyond it becomes forever hidden from the rest of the universe. Events may occur inside, but they can never be witnessed outside. From far away you cannot see the horizon itself. What you see is its effect. Light bent into arcs, matter spiralling inward in a bright, furious whirl before disappearing into the shadow. Cross that boundary, and the rest of the universe recedes behind you like a coastline fading at sea. No matter how powerful your engines, no matter how desperate your attempt, the horizon will not let you leave. The rules of general relativity say that once you pass this point, your fate is sealed. There are no side doors, no secret tunnels, no clever tricks. You are carried inward toward the singularity, and every possible path forward leads you there. For an object like a star or planet or a spacecraft, this is a physical trap. For information, the delicate patterns in matter and energy that tell the story of what fell in, it is a prison from which no message escapes. This is where the unease begins. In our everyday experience, losing track of something doesn't mean it no longer exists. If you drop a letter into a river, it's gone to you, but the paper still floats somewhere downstream. In quantum mechanics, this principle is elevated to a rule. Information cannot be destroyed. You can scramble it, you can hide it, you can transform it, but you cannot erase it completely from the universe. The event horizon seems to disagree. Drop a book into a black hole, and it is not just unreadable, it is gone, as though it never was. Drop a star in, and its intricate layers, its history, its orbiting planets, all of it is erased from the cosmic record, leaving only a slightly larger black hole in its place. It is the ultimate editor, crossing out entire paragraphs of the universe's story without leaving even a margin note. Stephen Hawking famously wrestled with this problem. In the 1970s, his work showed that black holes are not entirely black. They emit faint radiation due to quantum effects near the horizon. This Hawking radiation causes them to lose mass over incredibly long timescales, eventually evaporating altogether. But here's the troubling part. The radiation appears random, containing no trace of the information that went in. The black hole fades away, and with it, every detail about what it once contained. If this is true, then the laws of quantum mechanics, which have been tested in countless experiments, are violated. This is the black hole information paradox, and the event horizon is at the center of it. It is not just a physical surface, it is a philosophical cliff edge where our understanding of the universe's rules begins to crumble. For some physicists, this is an acceptable mystery, a sign that we still lack the theory to explain what happens at or beyond the horizon. For others, it is deeply troubling, a crack in the foundation that must be repaired. If our two most successful theories of the universe, general relativity and quantum mechanics, cannot agree on something as fundamental as whether information survives, then the picture we have built of reality is incomplete. This is where Gravastars re-enter the scene, like architects proposing a redesign of the door itself. In their structure, there is no true event horizon. Instead, the surface of the Gravastar sits just outside where the horizon would be. From far away, the difference is imperceptible, but up close, it changes everything. Matter falling toward a Gravastar would still accelerate as if approaching a black hole, but instead of slipping into a region of no return, it would strike the physical shell. The energy and information it carries would be stored or reflected, perhaps eventually radiated back into space. In this way, the Gravastar replaces the one-way door with something more like a locked gate, still impassable, but not erasing what passes through. The contents are hidden, but not annihilated. The story is preserved, even if it is never told again in the same form. Of course, this is still a hypothesis. We do not yet have the observational power to confirm whether any known black holes are actually Gravastars in disguise. But the idea has a certain elegance. It removes the singularity, softens the horizon, and lets the universe keep its rulebook intact. It feels less like a dead end and more like a room we cannot enter. Mysterious, yes, but still part of the same house. In the sessions to come, we'll turn to the paradox itself, the missing chapter in the Book of the Cosmos, and see how Gravastars might offer not only a rewrite, but a gentler ending. Think about a story you love. A novel, a film, a folk tale passed down to you. And imagine reaching the final chapter, only to find the pages have been torn out. The characters are frozen mid-action, the tension unresolved, and you are left staring at the last intact sentence, wondering what became of them. That is what the black hole information paradox feels like to many physicists. It's not simply that the ending is missing, it's that the entire record of the ending has been burned away. The paradox begins with a simple question. What happens to the information about the matter and energy that falls into a black hole? In our everyday lives, information can mean something as ordinary as a phone number, a recipe, or a memory. In physics, the word is more precise. It means the complete description of a system, the positions of its particles, the energies they carry, the way they interact. Even if you grind a piece of paper to dust or burn it to ash, the information it contained isn't truly lost. It's spread out into the arrangement of the ash, the motion of the smoke, the heat in the surrounding air. With enough detail, in principle at least, you could reconstruct what it once was. Black holes, according to classical general relativity, break this rule. Anything that crosses the event horizon is cut off from the rest of the universe. Once inside, the details of its structure, its composition, its history seem to vanish. All that remains for an outside observer is the black hole's mass, spin, and electric charge. Drop a diamond or a sack of coal into the same black hole, and from the outside they become indistinguishable. All differences are erased. This, by itself, is already strange. But it becomes a deeper problem when we combine it with Stephen Hawking's discovery that black holes can emit radiation. This Hawking radiation is not emitted from inside the black hole, but from the space just outside the event horizon due to quantum effects. Over unimaginable timescales, this process causes the black hole to shrink, to fade, and eventually to evaporate entirely. When the black hole disappears, the Hawking radiation it leaves behind appears to be purely random, a perfect thermal spectrum, carrying no trace of the information that once fell in. It's like opening a safe to find only a handful of unmarked coins with no record of what was stored inside. If this is true, then information is not just hidden, it is destroyed. And that is something quantum mechanics forbids. Physicists call this the black hole information paradox, and it has been debated for decades. Some have argued that perhaps the information is not destroyed, but somehow encoded in subtle patterns in the Hawking radiation. Others suggest it might be preserved on the event horizon itself, as though the surface of the black hole were a cosmic hard drive. Still others believe that the problem tells us we need a new theory of gravity, one that can reconcile the rules of the very large with the rules of the very small. The Gravastar model offers a gentle resolution to the paradox. In this picture, there is no event horizon, no absolute point of no return. Instead, the Gravastar has a physical surface, a thin shell of exotic matter, just outside where the horizon would be. Anything falling toward it would still be accelerated to incredible speeds. But instead of disappearing into an unreachable interior, it would strike the shell. The energy of the collision might be transformed into radiation and emitted back into space. The fine details, the information, could be stored in the structure of the shell itself, preserved instead of erased. It is not an exact analogy, but imagine again that missing chapter in your favourite book. In a black hole, the pages are destroyed. The story is gone. In a Gravastar, the chapter might be locked in a vault, inaccessible to you perhaps, but still intact, waiting in principle to be read again. The vault is sealed, but the words are not burned. One of the more intriguing aspects of the Gravastar idea is that its inner vacuum energy, the negative pressure at its core, plays a role in this preservation. The same gentle outward push that keeps the star from collapsing into a singularity also supports the shell that might carry the encoded history of everything that has fallen in. It is a kind of cosmic memory system, powered not by electricity or magnetism, but by the balance of space-time itself. This idea is not without its challenges. We do not yet know if such exotic matter can exist in the required form. We do not know how, or if, the information could actually be stored and released. But the concept has a certain harmony. It keeps the universe's commitment to information intact, it removes the mathematical infinities of singularities, and it replaces the finality of an event horizon with something more nuanced. And perhaps there is something comforting in that image, that even at the very extremes of gravity and density, the universe might choose to keep the story rather than erase it. That a Gravastar, quiet and dark though it may be, could be holding the record of every photon, every atom, every motion that has ever touched it. In the next part of our journey, we will step away from the theory for a moment and follow the life of a star, from its birth in a cloud of gas, through its long burning years, to the moment when gravity takes over and decides its fate. Only then can we see how a Gravastar might form in the first place, and why some stars may choose this quieter ending over the collapse into a true black hole. If you've ever watched a candle burn down to its end, you know there's a moment when the flame flickers, struggling to hold on before finally going out. A star's life, though it lasts millions or even billions of years, also has such a moment. A last flicker before its story changes forever. Stars are not eternal. They are born in cold clouds of gas and dust, where gravity gathers the material into denser and denser knots. Eventually, the pressure at the centre becomes so great that hydrogen atoms begin to fuse into helium, releasing light and heat. For most of a star's life, this nuclear fusion is a perfect balance against gravity's pull inward. The light pushes out, the gravity pulls in, and the star remains steady. But this balance cannot last forever. The star slowly burns through its fuel, fusing heavier and heavier elements in its core. For small stars like our Sun, this process ends quietly, with the outer layers drifting away to leave a white dwarf behind. For massive stars, many times the Sun's mass, the ending is much more dramatic. When the fuel runs out, gravity takes over completely. The star's core collapses at incredible speed, crushing atoms, forcing electrons and protons together into neutrons, and in some cases forming a neutron star. If the mass is too great, even the pressure from neutrons is not enough. In the traditional picture, nothing stops the collapse until it becomes a black hole, hiding all within an event horizon. But in the Gravastar scenario, something happens at the last possible moment, a change of mind, so to speak. Just before the collapse would pass the point of no return, the extreme conditions trigger a phase transition in the very fabric of space-time. It's not an explosion, not a sudden burst of light, but a subtle transformation. Instead of continuing inward to a singularity, the core becomes a bubble of vacuum energy, the same mysterious form of energy thought to be accelerating the expansion of the universe. This vacuum energy has an unusual property. It exerts negative pressure. Instead of pulling inward like gravity, it pushes outward. In the collapsing star, this push perfectly balances the inward pull, halting the collapse and holding the structure open. Around this core forms the thin, incredibly dense shell of exotic matter, the Gravastars' defining feature. From the outside, nothing seems different. The star has still undergone a catastrophic collapse. It still appears dark, with gravity so intense that light barely escapes. To a distant observer, it would be indistinguishable from a black hole, yet inside it is not a singularity. It is a stable, hollow structure, an object that has resisted gravity's final victory by changing the rules of the game. This idea draws comfort from the fact that nature often uses phase changes to solve problems. Water freezes into ice not because it becomes stronger, but because its molecules arrange themselves differently, forming a rigid lattice. Steel can be hardened or softened depending on how it is cooled. In the same way, space-time itself might freeze under extreme conditions, creating a stable, exotic form instead of a runaway collapse. It is a strange thought that the death of a massive star could lead not to a black hole but to something gentler, at least on the inside, still fierce in its gravity, still dark to the outside world, but without the singularity's infinite cruelty at its heart. Instead of becoming the perfect trap, it becomes something more like a vault, sealed, unyielding, but with its interior intact. The birth of a Gravastar, if it happens at all, would be rare. It would require a perfect combination of mass, collapse conditions, and perhaps quantum effects we do not yet fully understand. But even the possibility that such an object could form changes the way we look at those silent shadows scattered through the cosmos. We may not always be seeing black holes. Some of them might be stars that, in their final moment, decided not to fall all the way, that found a way to stop just short of the edge and hold their ground forever. In the next session, we'll peer closer at the ideas from quantum gravity and string theory that give this pause its scientific footing and see how the smallest threads of reality might weave a cocoon strong enough to hold a star open against the weight of its own gravity. If you were to hold a piece of fabric close to your eyes, you would see that what looks like a smooth surface from a distance is actually made of countless tiny threads, woven together in an intricate pattern. The universe is much the same. From the scale of galaxies and planets, space and time seem smooth, continuous, and unbroken. But zoom in far enough, to distances so small they make atoms look enormous, and physicists believe you would see that the fabric of reality has its own weave, its own pattern, perhaps even its own knots. Two of the most ambitious attempts to understand this weave are loop quantum gravity and string theory. They approach the problem differently, but both share the belief that space-time is not infinitely divisible. There is a smallest scale, a limit to how finely you can slice the fabric, beyond which the very idea of distance stops making sense. Loop quantum gravity imagines space-time as being made of tiny loops, linked together like an endless chainmail. These loops are unimaginably small, far beyond anything we could ever see directly, but they carry volume and area, giving space-time a kind of graininess. This approach suggests that gravity itself emerges from the way these loops connect, and that under extreme conditions, such as those inside a collapsing star, the weave can change its pattern entirely. String theory, on the other hand, starts with the idea that the fundamental building blocks of the universe are not points, but strings, minuscule filaments that vibrate in different ways to produce the particles and forces we observe. In this picture, the universe has more dimensions than we can see. perhaps 10 or 11 in total, and the strings hum quietly through this hidden architecture. The vibrations are the universe's music, and the notes determine the nature of everything, from light to gravity. What matters for the story of Gravastars is that both of these theories suggest space-time can undergo something like a phase change. Just as water can become ice or steam depending on the temperature and pressure, space-time might have multiple states. At ordinary densities, it behaves the way Einstein's general relativity describes. But when compressed beyond a certain limit, the pattern of loops or the tension of strings could shift into a new arrangement, one that resists further collapse. In the Gravastar model, this is the moment when a collapsing star's core transforms into a bubble of vacuum energy. It's not a violent tearing or a sudden explosion. It's more like a quiet crystallization, the loops tightening into a new configuration, or the strings settling into a different set of vibrations. The result is a stable, outward-pushing interior that can hold the rest of the structure open. This is not purely speculation. There are hints in both loop quantum gravity and string theory that such transitions are possible. In loop quantum gravity, for example, the extreme density of a collapsing star could trigger a bounce rather than a singularity, a reversal or halting of collapse caused by quantum effects. In string theory, certain configurations of strings, sometimes called fuzzballs, might replace the singularity and horizon entirely, spreading the mass and information throughout a complex structure. Gravastars fit naturally into this family of ideas, exotic, horizonless objects born from the smallest possible structures of space-time. We can think of it in terms of music again. Imagine an orchestra playing a slow, steady note. As the note continues, the musicians begin to change their tuning ever so slightly, until what seemed like a single tone becomes something richer, layered, and unexpected. The song is the same, yet different. That is what a phase change in space-time might feel like, a subtle shift that changes the meaning of the whole piece. Of course, we cannot test these ideas directly yet. The scales involved are far beyond our reach, and the mathematics is often dense and tangled. But these theories give us a language to describe what might otherwise be unimaginable. They allow us to say, yes, perhaps there is a way for a star to stop short of becoming a singularity. Perhaps the smallest threads of reality themselves refuse to be woven that tightly. And in that refusal, a new kind of star is born, one that looks like a black hole from afar, but whose heart is made of a frozen quantum fabric, pushing gently outward against gravity's pull. In the next session, we'll look at what happens when such a star spins or carries a powerful magnetic field, and how these hidden traits might reveal themselves to the universe in ways a true black hole never could. If you've ever watched water swirl down a drain, you've seen how rotation can shape the movement of everything around it. The closer the water gets to the centre, the faster it spins until the motion becomes a blur. In the depths of space, rotation works much the same way, though on a scale far beyond any sink or whirlpool. A spinning star, or a spinning gravastar, can twist the very fabric of space-time around it. Einstein's general relativity predicts this effect, known as frame dragging. When a massive object rotates, it doesn't just sit there in space, it tugs on space itself, pulling it along like a spoon stirring thick honey. Near the surface of such an object, this means that anything, even light, is carried forward in the direction of the spin. In black holes, this twisting can become so strong that there is a region, called the ergosphere, where nothing can remain still relative to the distant stars. A gravastar, if it spins, would have its own way of stirring space-time. The shell, that ultra-dense exotic matter boundary, would be in motion, dragging the space around it into a slow spiral. From a great distance, this effect would be hard to tell apart from a spinning black hole's influence. But up close, the behaviour might be subtly different. The absence of an event horizon means that certain patterns in the light or gravitational waves emitted near the object could carry a signature unique to Gravastars. Detecting such patterns is not easy, but it is one of the ways astronomers hope to distinguish between the two. Then there is magnetism, the quiet but powerful force that shapes much of the universe's structure. Magnetic fields are everywhere in space, from the Earth's protective shield to the colossal arc stretching out from active galaxies. In stars, magnetism is born from the movement of charged particles within, twisting and snapping in patterns we still don't fully understand. If a Gravastars shell carries an electric charge or conducts currents, it could generate a magnetic field unlike anything we have seen in ordinary stars. A particularly strong field could interact with surrounding matter, funneling it into jets, narrow beams of particles and radiation that shoot out at nearly the speed of light. Black holes are famous for these jets, which can stretch across thousands of light years. But in a Gravastar, the presence of a solid or semi-solid surface might change how these jets form and behave. Imagine a lighthouse on a foggy coast. A black hole's jet is like a beam of light from a tower with no windows. The light pours straight out from a single point, shaped entirely by the opening. A Gravastar's jet might be more like a beam sweeping past panes of uneven glass, refracted and bent in subtle ways before it escapes. From far away, both beams would still warn ships at sea, but the patterns of brightness and direction would not be quite the same. Some physicists have even speculated about magnetogravastars, objects where the magnetic field is so intense that it affects the stability of the shell itself. The field could reinforce the structure, making it more resistant to collapse, or in certain cases destabilize it, causing pulses or outbursts. These magnetic interactions might leave fingerprints in the form of unusual X-ray or radio signals, giving astronomers a clue that they are looking at something stranger than a black hole. Rotation and magnetism can also work together in fascinating ways. A spinning Gravastar with a strong magnetic field could, in theory, launch particles from its poles with incredible energy, lighting up the surrounding space. It might also shed energy more slowly than a black hole, since the shell could radiate heat and particles directly. Over time, these processes could give the Gravastar a kind of aging, not in the way living things age, but in the way a bell's tone slowly fades as the vibrations within it diminish. These ideas remain in the realm of theory, but they are not pure fantasy. Astronomers are already watching the skies for the telltale signs. Small deviations in the timing of gravitational wave echoes after massive collisions, unexpected structures in the light curves of accretion disks, magnetic signatures that don't quite match black hole models. Each observation is like a puzzle piece, and while we do not yet have the full picture, the edges are starting to take shape. If Gravastars exist, their rotation and magnetic fields could be some of the few ways we might prove it. They are, after all, masters of disguise, outwardly identical to black holes in mass and silhouette. But even the best disguise can slip if you know where to look. The way a Gravastar stirs space-time, the way its shell and magnetic field work together, might just be the detail that catches the universe in the act of showing us something new. In the next session, we'll move from the grand, swirling forces of rotation and magnetism to something more intimate, the idea that a Gravastar might have a pulse, a gentle rhythm in the darkness, sending whispers through space-time in the form of gravitational wave echoes. If you've ever rested your head against someone's chest and felt the slow, steady rhythm of a heartbeat, you know how reassuring a gentle pulse can be. It is a sign of life, a quiet reminder that something within is moving, breathing, continuing. Most stars, once their fiery light is gone, have no such rhythm. A neutron star might spin rapidly, flashing its beams like a cosmic lighthouse, but a black hole falls utterly silent, absorbing everything and revealing nothing. A Gravastar, though, might be different. The idea is simple enough to imagine, though the reality would be unlike anything we have ever experienced. If the exotic matter shell of a gravastar is stable, but not perfectly rigid, it could respond to changes in pressure or external impacts with a kind of oscillation, a swelling and contracting so faint and slow that it would be imperceptible to the human senses but real nonetheless. Think of a drum skin stretched tight. Strike it, and it vibrates in complex patterns. Even without a visible hit, changes in tension can make it hum softly in ways only the most sensitive instruments can detect. In a gravastar, the strike might come from matter falling onto the shell, a stream of gas from a nearby star, a passing asteroid, or the remains of a collision. The impact would send a ripple through the structure, a pulse that could travel all the way around its circumference before fading. These oscillations, in turn, could disturb the surrounding space-time enough to produce what physicists call gravitational waves. Faint, rippling distortions in the fabric of the universe itself. We have already learned to listen for gravitational waves. The LIGO and Virgo detectors have picked up the subtle stretching and squeezing of space-time from colliding black holes and neutron stars, events so powerful they can be felt across billions of light-years. But the signal from a gravastar's pulse would be different. Instead of the clean, sharp chirp of a collision, it might arrive as a faint echo, a repeated, slowly fading pattern that follows the main event. Imagine shouting into a canyon. The first echo returns quickly, strong and clear, but if the walls of the canyon are irregular, you might hear a series of softer echoes after the first, each a little more distorted and delayed. A black hole collision, in theory, should produce a single clean ring down, a final gravitational note, as the new black hole settles. But if the merged object were a gravastar, the shell could act like those canyon walls, bouncing the waves back and forth inside, letting them leak out in faint, delayed whispers. These gravitational wave echoes are one of the most intriguing observational clues in the search for gravastars. A few tentative hints have appeared in LIGO's data, but nothing yet has met the rigorous standards of scientific certainty. The signals are faint, easily lost in the background noise, and the universe offers us no shortage of things that can mimic them. Still, the possibility is there, waiting for better instruments and sharper listening. The pulse of a gravastar, if it exists, would not be a heartbeat in the biological sense, but it might serve a similar purpose in the cosmic narrative. It would be a rhythm where we expected stillness, a sign of activity in a place we assumed was forever silent. In a way, it would mean that even in the darkest, most extreme environments, there can still be a kind of motion, a whisper of persistence against the crushing quiet. And while the gravitational echoes might be our best hope of detecting such pulses directly, they might also have more subtle effects on the light and matter around the gravastar. If the shell expands and contracts ever so slightly, it could change how infalling material spreads or heats. It might create flickers or variations in the accretion disk, the swirling, luminous ring of matter falling toward the object that don't quite match black hole models. This is what makes the gravastar such an enticing possibility for astronomers. It isn't just an alternative to the black hole, it's an object with a different personality. The black hole is a silent end, a point beyond which all paths vanish. The gravastar, for all its darkness, might have a hidden inner life, a pulse, a capacity to store and release information, a subtle way of interacting with its surroundings. In the end, the idea of a pulsing gravastar reminds us that the universe often hides complexity behind simplicity. From a distance, it might appear no different from any other dark, massive object. But draw close in thought, if not in person, and you might sense the quiet rhythm of something that refuses to be entirely still. In the next part, we'll step back from the theoretical and begin exploring what signs astronomers are actually searching for in the night sky, and how, with each new observation, we might catch a gravastar revealing itself. if only for a moment. If you've ever seen a shadow on a foggy evening, you know that its edges are not as sharp as they are in bright daylight. The light scatters, the darkness blurs, and you can't quite tell where the shadow begins or ends. Looking at a black hole is a bit like that. Not because we can see the object itself, we can't, but because of how light bends and swirls around it before disappearing. In 2019, the Event Horizon Telescope, a network of radio observatories spread across the Earth, gave us something extraordinary. The first direct image of a black hole's shadow. It was not a photograph in the ordinary sense, but a map of radio light collected over days, processed through complex algorithms, and assembled into that now famous image, a hazy, glowing ring with a darker centre. That shadow is not the black hole itself, but the absence of light from the region, where its gravity has trapped everything, even photons. The glow comes from the hot, swirling matter in the accretion disk, gas and dust spiralling inward, heated to millions of degrees as it approaches the point of no return. Around a black hole, gravity bends light into a nearly perfect circle called the photon ring, a narrow band where photons orbit before either falling in or escaping. The dark centre we see is the silhouette of the event horizon against this glowing backdrop. If a Gravastar were sitting where we think a black hole is, the view through the Event Horizon Telescope might look almost identical. Its gravity would still be immense, bending light in nearly the same way. The photon ring would still form, tracing a bright halo around a shadowy middle. From a distance of millions or billions of light years, the differences between the two might be subtle, almost invisible to the eye. But they might be there. A Gravastar has no event horizon, only a solid or ultra-dense shell just outside where the horizon would be. Light that would otherwise vanish forever might instead strike that shell and reflect, scatter, or be re-emitted in ways slightly different from a black hole's behaviour. This could make the photon ring a little thicker, or cause its brightness to vary in patterns not quite matching our black hole models. It's a bit like looking at two lanterns from far away. Both are dim and shrouded in mist, but one has glass that's just a little uneven. The light it throws is almost the same, yet here and there you catch a shimmer that seems out of place, a flicker where the other lantern stays smooth. Astronomers study the black hole images from the Event Horizon Telescope in much the same way, looking for tiny asymmetries, subtle shifts in brightness, or faint structures in the glow. So far, we haven't found anything in those images that demands a Gravastar explanation. The black hole in the galaxy M87, and later the one at the centre of our own Milky Way. Both match general relativity's predictions well. But the resolution we have now is only the beginning. As the telescope network expands, and as image processing techniques improve, we may be able to see more detail. Enough to tell whether the darkness in the middle is truly an event horizon or something else entirely. It is worth remembering that nature does not hand us its secrets easily. Even if Gravastars exist, they are experts at mimicry. Their shadows could be almost perfect imitations, their light rings nearly indistinguishable from those of black holes. Detecting them will require not just sharper vision, but careful patience. The willingness to look at the same glow for years and notice the smallest of changes. And perhaps that is fitting. If Gravastars are indeed the universe's quiet rebels, objects that have chosen to stop just short of becoming true black holes, then it makes sense that they would leave only the faintest trace of their defiance, hidden in the shape of their shadow. In the next session, we will turn from images to sounds, or rather, to the vibrations of space-time itself, and see how scientists are listening for whispers after the great crashes of the cosmos. If you close your eyes on a still evening and really listen, you'll notice that silence is never truly silent. There are the faintest sounds, a distant hum of traffic, the creak of wood in the walls, the soft whisper of your own breathing. Sometimes, what you notice is not the first loud sound, but the small echoes that follow it. In the cosmos, scientists have learned to do something similar, not with ears, but with instruments that can feel the trembling of space itself. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves for the first time. These ripples in space-time, predicted by Einstein a century earlier, are produced by some of the most violent events in the universe, the collision of massive objects like neutron stars and black holes. When such a merger happens, the waves spread outward at the speed of light, stretching and squeezing space by tiny amounts. By the time they reach Earth, the distortion is smaller than the width of a proton, yet sensitive detectors can still measure it. The signal from a black hole merger has a particular shape. It rises in frequency and amplitude as the two objects spiral toward each other, then peaks in a sharp burst when they collide. After that comes the ring down, a single fading note as the new black hole settles into a stable shape. It is a cosmic full stop, a sign that the event is over and the object has gone quiet forever. But what if that final silence is not quite so final? The Gravastar hypothesis suggests that, instead of an event horizon swallowing all vibrations, the newly formed object could have a surface, an ultra-dense shell capable of reflecting gravitational waves back and forth inside itself. Some of that energy might escape in the form of faint delayed signals, gravitational wave echoes. These echoes would not be loud. They would arrive seconds or fractions of a second after the main merger signal, each weaker and more distorted than the last. Imagine dropping a stone into a deep well. The initial splash is the merger. The echoes are like faint plinks you hear afterward as drops of water fall from the walls, each sound carrying the memory of the original impact but altered by its journey. Detecting such echoes is incredibly challenging. The main merger signal is strong and unmistakable, but the echoes hide within the noise, random fluctuations from the detectors themselves, seismic activity from the Earth, and countless other small disturbances. Scientists use complex algorithms to search for repeating patterns in this background, looking for something that matches the timing and frequency shift a gravastar would produce. There have been hints. In 2016, just after the first LIGO detection was announced, a group of researchers reported finding a pattern in the data that could be interpreted as echoes. Later analyses questioned this interpretation, suggesting the pattern might have been a coincidence or a product of the analysis method. Since then, new gravitational wave events have been scrutinized in the same way, with occasional whispers appearing in the results, but nothing yet that everyone can agree on. Even so, the search continues, each new observing run by LIGO, Virgo, and now KAGRA, a Japanese gravitational wave detector, adds more data, more cosmic crashes to examine. As the detectors are upgraded and made more sensitive, the faintest echoes will become easier to hear. In the future, planned observatories like the space-based LISA mission will listen for gravitational waves at different frequencies, perhaps revealing features that ground-based detectors cannot. If we do detect echoes with confidence, it would be one of the strongest pieces of evidence against the existence of event horizons, and therefore in favour of gravastars or other exotic horizonless objects. The echoes would tell us that something is bouncing gravitational waves back instead of letting them vanish into infinite silence. Of course, the universe has a way of surprising us. Even if we find echoes, they may have explanations we haven't thought of yet. Nature can be tricky like that, offering clues that seem to point one way but lead somewhere else entirely. This is why scientists treat each detection with such care, checking and rechecking before drawing conclusions. But there's something quietly beautiful in the thought itself, that after the great violence of a cosmic collision, the universe might not be entirely done speaking, that instead of a sudden cut to black, there could be a series of fading notes, a reminder that even in endings there can be afterthoughts, reverberations and whispers. In the next session, we'll turn our attention to a different kind of observation. Not the listening for faint tremors in space-time, but the watching of matter itself as it swirls, heats, and sometimes crashes into whatever lies as the centre. Here, in the dinner table of the cosmos, the difference between a black hole and a gravastar might be revealed in what is served and what is left behind. If you imagine the universe as a vast dining hall, then black holes and gravastars have some of the most dramatic tables. Their guests are not people, of course, but streams of gas, dust, and even entire stars, drawn in by the irresistible pull of gravity. These feasts are not leisurely affairs. The food, matter from the surrounding space, arrives at extreme speeds, whipped into a spiral as it falls inward, colliding with itself, heating up, and giving off light and radiation before reaching the main course. Astronomers call this glowing, swirling ring of material the accretion disk. It is a place of intense activity, where matter that might have drifted in cold darkness for millions of years is suddenly heated to millions of degrees. At these temperatures it shines brilliantly in X-rays, ultraviolet light, and sometimes visible light as well. The accretion disk is, in a sense, the only part of a black hole we can truly see, because the black hole itself, or a gravastar, remains hidden behind its shadow. For a black hole, the accretion disk is a one-way trip. Matter that gets too close passes the event horizon and disappears forever, its energy radiated away in the final moments before crossing the threshold. The last thing it emits is determined entirely by the gravitational physics at the edge of that horizon. Once past it, there is nothing more to observe. A gravastar changes the ending of this story. Without an event horizon, there is a solid or ultra-dense surface waiting just outside where the horizon would be. Matter spiraling inward doesn't vanish into infinity. It crashes into this surface. The collision is violent, converting kinetic energy into heat, light, and other forms of radiation. Depending on the properties of the shell, some of this energy might bounce back outward, producing flashes or bursts unlike those from the black hole's edge. You could think of it like dining at two very different tables. At the black hole's table, every dish vanishes the moment it is served, the flavours lost forever in an unseen place. At the gravastar's table, the dishes arrive and crash into a wall of mirrors. The impact sends bits and pieces scattering, some returning to the dining room for everyone to see, though changed by the force of the collision. This difference could, in theory, show up in the light we observe. Black holes have a well-modelled relationship between how bright their accretion disks are and how material behaves near the event horizon. If an object is slightly brighter, or if it produces unexpected high-energy bursts, it might hint at a surface. The timing of these bursts could also be a clue. The light might arrive in sharp spikes, or with delays that reflect the travel time between the impact site and the point where the radiation escapes. Jets are another part of the picture. Many black holes launch narrow beams of matter and energy from their poles, powered by the intense magnetic fields in the accretion disk. A gravastar could also produce jets, but the mechanics might differ if the shell's surface interacts with the inflowing material. This could change the jet's structure, its brightness, or the way it flickers over time. Telescopes that can watch in multiple wavelengths, from radio to gamma rays, are particularly important here. By studying the spectrum of light coming from the accretion disk, astronomers can look for patterns that don't match black hole predictions. A gravastar's surface might, for example, heat in falling material to slightly different temperatures, changing the balance between X-rays and ultraviolet light. These differences might be tiny, but with careful observation, they could be enough to raise suspicion. Some scientists have also speculated about a more exotic possibility, that matter striking a gravastar's shell could create oscillations in the surface itself, like a gong being struck. These oscillations might couple to the surrounding plasma in the accretion disk, creating repeating patterns of brightness that would be absent around a black hole. If such periodic signals were detected, They could be a unique fingerprint of a gravastar. So far, most observations of accretion disks around suspected black holes match the black hole model well. But match in astronomy doesn't always mean prove. It simply means we have not yet found a deviation large enough to demand a new explanation. Given how subtle the differences might be, it's possible that some of the objects we have been calling black holes for decades are actually gravastars, their secret hidden behind the blinding light of their dinner tables. Watching an accretion disk is a little like watching the flame of a candle through a fogged window. You can see it flicker and glow, you can guess at its shape, but the glass blurs the details. It takes time, patience, and the right instruments to notice if the flame behaves differently from what you expect. And so, astronomers keep watching, not just for brightness, but for the way the light changes from moment to moment, for the faint bursts that might follow an unseen collision, for the patterns that whisper, "This is not an ordinary feast, and the host is not who you think." In the next session, we'll explore another way a gravastar could betray its presence. Not through what happens when matter falls in, but through light that was trapped long ago and is only now finding a way out, arriving late to the cosmic stage. If you have ever been at a concert, you might have noticed that the music and the image of the performer do not always arrive at the same time if you're far from the stage. You see a hand rise for the drum beat before you hear the sound. The light reaches you instantly, but the sound takes longer to cross the space. In the universe, we often think of light as the fastest messenger, and it is. But even light can be delayed, not because it slows down, but because of the paths it must take and the places it can be trapped. Black holes are the ultimate traps for light. Once a photon crosses the event horizon, it can never return. Even light skimming just outside the horizon can be forced into a precarious orbit in the photon ring, circling the black hole many times before escaping. But it always leaves promptly compared to human timescales. Once it gets out, it races across the cosmos. Gravastars, on the other hand, might offer a stranger possibility. Without an event horizon, there is no point beyond which escape is impossible. But there is still an ultra-dense shell that can interact with light in unusual ways. If photons fall toward the gravastar and encounter the shell, some could be absorbed, some reflected, and some scattered into new paths that keep them circling inside the object's gravitational well for a long time before they finally find their way out. In theory, this could mean that light emitted by matter long ago might still be trickling out today, not in a steady glow, but in irregular flashes or faint glimmers, each carrying the memory of an earlier event. The effect would be subtle, easily mistaken for other cosmic phenomena. A sudden brightening of a distant object, a short-lived flash in a galaxy's core, could be explained by many things. A star being torn apart, a jet flickering, or even the aftershock of a collision. But if the timing and spectrum of the light were just right, they could hint at delayed photons escaping a gravastar's grasp. It is not easy to picture how light can be trapped without an event horizon, but you might think of it like a hall of mirrors. A photon inside the gravastar's strong gravitational influence could bounce back and forth, its path bent again and again by the curvature of space-time and the reflective properties of the shell. With each bounce, it loses a little energy, shifting toward redder wavelengths, until finally it slips away, weakened but free. By the time it reaches our telescopes, it might seem oddly faint or stretched in colour compared to light from similar events. Another way to imagine it is as a drop of water in a network of narrow channels. The drop might take the most direct path and reach the end quickly, or it might wander through side passages swirling in eddies before finally emerging. In the universe's vast darkness, these meandering paths for light could last seconds, hours, or even years, depending on the scale. If astronomers could spot such delayed signals, they might be able to tell whether an object has a true event horizon or something else. A black hole has no way to return photons once they are lost. A gravastar's shell could, at least in principle, send some back, though much later and in altered. Form detecting this would require patient watching, recording bursts and flickers over long periods, and comparing them with the predicted behavior of black holes. There is also the possibility of light being trapped in layers of plasma surrounding the gravastar before escaping. The shell could be coated in an atmosphere of ionized gas, where light is absorbed and re-emitted many times before it leaves. Each re-emission shifts the light's properties slightly, creating a spectral fingerprint that might differ from that of a black hole's surroundings. This would be like hearing a familiar song played through layers of echo and distortion, still recognizable, but with a texture that tells you it has travelled through a complicated path. The challenge is that space is full of things that can delay or distort light. Dust clouds, magnetic fields, and turbulent gas can all produce effects that mimic what a gravastar might do. Separating these influences requires not just sharp instruments, but careful reasoning, a kind of cosmic detective work where every clue must be weighed and tested. Yet, the appeal of the idea is hard to ignore. There is something poetic about the thought that light from a moment long past might still be arriving, slipping out of a hidden prison in the heart of a distant galaxy. We could be watching a flicker tonight that began its journey when life on Earth was still in its earliest forms, only to be held, delayed, and finally freed by a structure we do not yet fully understand. If we ever confirm that such delayed light exists, and that it comes from a gravastar, it would change the way we think about these dark giants. They would no longer be silent, final destinations for matter and energy. They would be keepers of long-held messages, releasing them slowly into the cosmos, not in a rush, but in patient intervals, as if telling us that some stories are meant to be heard only after the longest of waits. In the next part, we'll step back from these specific clues and look at the bigger picture, the bold cosmological implications of Gravastars, and what it might mean if some of the most massive, mysterious objects in the universe are not what we thought they were at all. Every spiral in the night sky, every great glowing city of stars seems to have a deep, dark anchor at its centre. For decades, astronomers have believed that these anchors are supermassive black holes, objects millions or billions of times the mass of our Sun, their gravity holding together the orbits of entire galaxies. We have names for them now: Sagittarius, a star in the heart of our Milky Way, M87 star in the giant elliptical galaxy, whose shadow we first saw with the Event Horizon telescope. These black holes are thought to shape their galaxy's growth, feeding on surrounding matter, launching jets of energy, and stirring the cosmic environment like a spoon in a vast bowl of stars and gas. But what if they are not black holes at all? What if, in place of an event horizon, they have a surface, a shell, and a heart filled with dark energy? What if these galactic anchors are gravastars? The difference would not be visible in the casual sense. If you were to drift past Sagittarius, a star, its pull on you would be the same whether it were a black hole or a gravastar. The orbits of nearby stars would trace the same elegant curves, their periods the same, their accelerations unchanged. The glow of infalling matter, the shadows in the light, would all seem to agree with the black hole picture, at least at first glance. Yet if Sagittarius, a star, were a gravastar, the story of the galaxy's centre would subtly shift. A black hole is a one-way drain for matter and energy. Whatever falls in is lost to the universe, locked away beyond reach. A gravastar, by contrast, could allow some of what it consumes to be returned, in light, in heat, perhaps even in particles, over long spans of time. This would make the heart of the galaxy less of a vault and more of a slow, deep reservoir, one that leaks and breathes in ways we're only beginning to imagine. The presence of a gravastar at the centre of a galaxy could also change the rules of galactic evolution. Supermassive black holes are often credited with regulating star formation by releasing energy into their surroundings. If gravastars release energy differently, perhaps more gradually or in pulses, the rhythm of star birth and death across a galaxy might be altered. Whole generations of stars could form under slightly different conditions, and over cosmic timescales, that small difference could ripple outward into the shape and brightness of the galaxy itself. It's tempting to think of the centers of galaxies as static, the immovable points around which everything else turns. But if gravastars occupy those places, they might be less like anchors and more like hidden engines, quietly cycling matter and energy through forms we cannot yet see. They could store information too in ways black holes cannot, their surfaces preserving imprints of everything they have ever touched. In a sense, the gravastar would be the galaxy's memory, a place where the record of its history is not erased but archived. We don't yet have the instruments to be certain. The data we have from Sagittarius A star and M87 star fits the black hole model well. But the Gravastar model fits too if you're willing to see it. The differences are buried in the details, in the faintest echoes of gravitational waves, in the most subtle variations in the photon ring, in the slight deviations in how light curves through the space around them. Perhaps one day, with sharper eyes and quieter detectors, we will learn that the darkest hearts of galaxies are not silent abysses, but something more complex, something that holds the universe's most closely guarded stories, waiting for the right moment to let them slip back into the light. In the next session, we'll follow that idea further, imagining gravastars not only as keepers of secrets, but as recyclers, cosmic machines that take in the old and give it back in new forms, refusing the finality of disappearance. If you stand at the edge of the sea and watch the waves, you see a rhythm that never ends. Water comes in, water goes out. It is never quite the same water, but the ocean never empties, never stays still. It is a cycle, a return. In the deepest sense, nature loves to recycle. Leaves fall and rot, their nutrients feeding the roots of the next generation of trees. Stars live and die, scattering the elements that will one day become new stars, planets, and even living beings. Black holes, in our traditional picture, seem to break this rule. They are the final stop for matter and energy, the last page of the story. What falls in does not return. The gravitational pull is so absolute that, once you cross the event horizon, you are gone from the visible universe forever. It is an ending without a return. But gravastars would change that ending. Without an event horizon, they would be less like locked vaults and more like deep, complex machines, not designed by anyone but shaped by the physics of space-time itself, that take in matter, hold it, and then give some of it back in a transformed form. They could be, in their own strange way, cosmic recycling plants. Imagine a star wandering too close to a gravastar. Gravity pulls it apart, stretching it into a long, thin stream of gas. Some of this gas spirals inward, slamming into the gravastar's shell. On a black hole, this is where the story stops. The gas disappears, leaving only the heat and light it emitted before crossing the horizon. But on a gravastar, that shell is not a one-way door. It can reflect, scatter, and reprocess the energy. Over time, particles and radiation could leak back into space, carrying traces of the star that was consumed. It might happen slowly, not in dramatic bursts, but in a patient, measured rhythm, a soft return of energy, like steam escaping from a closed pot. That return could take the form of faint light, heat, or even exotic particles that travel across the galaxy. In this way, gravastars could be steady contributors to the energy balance of their surroundings, feeding back into the galactic ecosystem instead of sealing everything away. On a grander scale, this means that gravastars could play a subtle but important role in cosmic evolution. Galaxies need both creation and destruction to maintain their structure. Too much energy trapped in black holes would reduce the fuel available for new stars and planets. Too much energy released too quickly could strip galaxies of the gas they need to form stars at all. A gravastar's slower, gentler release might provide a kind of regulation, keeping the galactic cycle in balance over billions of years. This recycling could also extend to information, not just in the abstract mathematical sense used in physics, but as real, physical imprints of everything that has fallen in. A black hole's event horizon erases the details. The laws of quantum mechanics protest this, but in the classic picture, the information is gone. A Gravastars surface, however, could keep that record, a vast library etched into the arrangement of its exotic matter. Every atom, every photon, every piece of dust that has ever touched it might leave behind a trace, woven into its structure. The energy that eventually escapes would carry hints of that record, subtle and encoded, but still there. If this is true, Gravastars could act as archivists of the universe, not only returning matter and energy, but also preserving the memory of where they came from. The light and particles they emit might be, in some deep sense, the retelling of old stories, even if we cannot yet read the language. It's worth remembering that recycling in nature often changes the thing being recycled. Fallen leaves do not return as leaves, they return as soil. A wave that retreats from the shore is not the same shape, not the same arrangement of water, as the one that came in. In the same way, what comes out of a Gravastar would not be exactly what went in. The matter might be transformed, broken down into simpler particles, or altered by the intense conditions inside the shell. But the fact that something returns at all would make them unlike black holes in a profound way. There is a quiet elegance in this vision. Gravastars as patient, dark engines in the galaxy, taking in the excess, releasing what they can, and keeping the rest safe for times and places we cannot yet imagine. They would not roar like quasars or flare like supernovae, but hum quietly over eons, a background presence in the cosmic cycle. In the next session, we'll follow this line of thought into even more mysterious territory. The possibility that Gravastars are not just part of the visible universe, but may be hiding in the shadows of one of the greatest puzzles in physics: dark matter. If you walk into a room at night and turn on a single lamp, you will see the things the light touches. The corners that stay dark are still filled with objects: a chair, a bookshelf, a forgotten jacket draped over the arm of a chair. But they are invisible to you until you reach for them. In much the same way, astronomers have discovered that the universe is filled with something we cannot see, something that outweighs all the stars and gas we can observe. We call it dark matter, not because it is sinister, but because it does not emit or reflect light in any form we can detect. We know dark matter must be there because of the way it pulls on everything else. Galaxies spin too fast to be held together by visible matter alone. Clusters of galaxies bend the light from objects behind them more than they should if we counted only the stars we can see. The missing mass, this hidden gravitational glue, makes up roughly 85% of the matter in the universe. And yet, after decades of searching, we still don't know what it is. Most ideas about dark matter imagine it as exotic particles, massive but invisible, drifting through space without interacting with ordinary matter except through gravity. But there is another, quieter possibility. What if some portion of dark matter is not made of particles at all, but of objects, massive, compact, and almost perfectly disguised? This is where Gravastars step into the shadows. By their very nature, they would be hard to tell apart from black holes in most observations. They would give off little to no light except in special circumstances, and their gravity would be the same for a given mass. If there were enough of them scattered across the universe, not just at the centres of galaxies, but drifting through the intergalactic darkness, they could contribute to the unseen mass we attribute to dark matter. The idea is not without precedent. Astronomers have long considered the possibility that some of the dark matter might be in the form of MACOs, massive compact halo objects, such as faint stars, brown dwarfs, or black holes lurking in the halos of galaxies. Gravastars could fit into this category, though with very different internal structures from black holes. To imagine how they might hide, picture a set of heavy stones lying under the surface of a lake. The water moves over them as though they were not there, You only know they exist because the current bends around them in subtle ways. Gravastars, in this analogy, would be the submerged stones in the currents of space-time, their presence known only through the way they influence the orbits of stars and galaxies. If gravastars formed frequently in the early universe, perhaps as a common alternative to black holes when the first massive stars collapsed, there could be far more of them than we realize. They might drift in deep space, far from the bright regions where our telescopes tend to look. Because they are dark and compact, they could pass through regions of space unnoticed, their gravity blending into the great invisible pattern we call the cosmic web. Detecting such gravastars would be an immense challenge. Microlensing, the bending of light from a background star as a massive object passes in front of it, could reveal their presence. But microlensing events are rare, brief, and difficult to study in detail. Still, large surveys like OGLE and the upcoming Vera Rubin Observatory could, over time, collect enough of these events to hint at whether gravastars are among the hidden population. If even a small percentage of dark matter turned out to be gravastars, it would change how we think about the cosmic balance sheet. Dark matter would no longer be entirely exotic and particle-based. Part of it would have a complex internal story, a surface, perhaps even a slow interaction with the universe through returning matter and energy. The invisible would become a little less mysterious, replaced not with something entirely known, but with something at least partially understood. There's a certain quiet beauty in that thought, that some of the universe's most elusive mass might be hidden in objects that are already strange in themselves. Gravastars would not only solve some of the puzzles posed by black holes, but they could also take their place among the great invisible architects of cosmic structure. They would be the quiet, massive companions of galaxies, unseen but profoundly influential, holding shape in the dark the way bones hold the form of a body beneath the skin. And if gravastars do make up part of dark matter, then they are everywhere, not just at the hearts of galaxies. They could be drifting between galaxy clusters, passing silently near planetary systems, even moving through the outer reaches of our own galactic halo. We would never notice, unless they chose, in some rare moment, to reveal themselves with a flicker of light or a faint gravitational whisper. In the next session, we'll take the boldest leap yet, imagining that we're not just surrounded by gravastars, but that we might be inside one, that our entire universe could be the interior of a structure like this, its shell beyond the reach of our vision, holding everything we know within. Every so often, a scientific idea comes along that feels less like a theory and more like a whisper from the edge of imagination. It doesn't just describe the universe, it rearranges your sense of where you are in it. The notion that our entire universe could be inside a gravastar is one of those ideas. In the standard picture of a gravastar, you have a dark energy core wrapped in a thin, dense shell of exotic matter. From the outside, it might look like a black hole, its gravity bending light in the familiar way. But on the inside, instead of a singularity, there is space, not empty, but expanding, filled with energy. To an observer inside, that space could feel vast, stretching far beyond the shell's boundary, with no visible edge. In other words, it could feel a lot like a universe. If that sounds far-fetched, consider this. Our own universe is expanding, and the expansion appears to be driven by dark energy, a mysterious force that accelerates the growth of space itself. A gravastar's core is also modelled as being filled with dark energy, which pushes outward against the shell. The parallel is hard to ignore. From this perspective, the Big Bang might not have been the birth of everything, but the moment a gravastar formed in a larger reality. The explosion we describe could be the rapid inflation of its dark energy core. Everything we see, stars, galaxies, even the cosmic microwave background radiation, would be part of the interior landscape of this gravastar, existing entirely within its shell. Outside, in that larger reality, it would be just one compact object among perhaps countless others. The mind easily slips toward questions here. If we are inside a gravastar, what is outside? Is it a place with its own galaxies, its own laws of physics, its own observers? Could there be layers upon layers of such structures, universes nested inside gravastars inside other universes, like cosmic Russian dolls? This framing also changes how we think about time. Inside the gravastar, time would be measured by the expansion of space and the evolution of its contents, just as we experience it now. But from the outside, time might run differently, or even appear to slow down. To an external observer, the events unfolding inside might look frozen or distorted, while to us they feel natural and continuous. Of course, the idea is highly speculative. It comes from noticing patterns between gravastar models and certain cosmological equations, then daring to connect them. There's no direct evidence that we live inside such a structure, but it is not impossible according to the mathematics we use to describe both black holes and expanding universes. The geometry of space-time allows for such arrangements. Nature simply hasn't told us yet whether it chooses them. Even if it is only a thought experiment, there is something quietly profound in the idea. It makes the boundary between inside and outside feel less absolute. We might think of the universe as infinite and self-contained, yet it could be part of something else's interior. And if that's true, then our own universe could also give rise to gravastars, each holding its own internal cosmos. Creation and enclosure would become two sides of the same coin. It also invites a gentler perspective on our place in the cosmic order. If the universe is the inside of a gravastar, then everything we know exists within something that is, in a sense, protective. The shell that holds it is not a prison, but a structure that makes the space inside possible. Without it, the dark energy might dissipate and the interior would collapse. The boundary would be what gives the universe form. You can think of it like living inside a vast, unlit cathedral. You never see the walls, but their presence shapes the space, the acoustics, the way sound and light move. The walls hold the silence in place. In the gravastar analogy, the shell is that invisible architecture, shaping the cosmic interior without revealing itself to those within. It is a reminder that even the largest thing we know, the universe itself, might be part of a larger story. We may be inside something, and that something may be one of many. Perhaps, far beyond our cosmic horizon, the outer surface of this gravastar glows faintly in another sky, in a place where someone else is wondering about the structure at the heart of their galaxy, not knowing it contains us. In the next session, we'll step back from the sheer vastness of that speculation to something closer to the heart of physics, the possibility that gravastars could offer a softer, more harmonious ending for the two great theories that have long struggled to coexist: Einstein's general relativity and quantum mechanics. For more than a century, physics has been telling two great stories about the universe, and although both are brilliant, they have never quite agreed on how the tale should end. One is Einstein's general relativity, which describes gravity as the bending of space-time by mass and energy. The other is quantum mechanics, which explains the strange, probabilistic behaviour of particles on the smallest scales. Each is tested, trusted, and essential. And yet, when we try to apply them both to the same extreme place, such as the centre of a black hole, they clash. Relativity says the collapse of a massive star leads inevitably to a singularity, a point where density becomes infinite and the known laws of physics break down. Quantum mechanics, on the other hand, insist that information cannot be destroyed, and infinities like singularities are unphysical. In other words, relativity imagines an ending where the story simply stops mid-sentence, while quantum mechanics demands that nothing in the story is ever truly lost. This is the tension at the heart of the black hole information paradox, a paradox that has kept physicists awake at night for decades. It is not simply a matter of detail, it is a matter of principle. If we cannot reconcile these two great theories, we cannot claim to have a full understanding of reality. The Gravastar model offers a different ending, one that does not require either theory to be discarded. In a Gravastar, the inward collapse of matter is halted just before the formation of an event horizon, thanks to the repulsive effect of a dark energy core. The shell that forms around this core is made of exotic matter, with properties that can be described using both relativity and quantum field theory. Instead of a singularity, you have a stable, finite structure. Instead of infinite density, you have a measurable pressure and an energy density that never exceeds certain limits. In this way, relativity still governs the overall shape and gravitational pull of the Gravastar, while quantum mechanics can still preserve information at the surface. There is no point in the space-time where the mathematics breaks completely. It is a gentler, more collaborative conclusion, not a collision between theories but a handshake. If this picture is correct, then the violent full stop of a black hole becomes something more like an ellipsis. Matter and energy do not vanish beyond a horizon. They meet a boundary where they can interact with the quantum nature of space, storing information instead of erasing it. Over long timescales, that information can be released, not instantly, but slowly, like the fading echoes of a song. It is worth pausing to note the emotional difference between these endings. The singularity is an end without appeal, a place we cannot see, cannot describe, cannot reach. It is the physics equivalent of a locked room where all our questions are thrown away. A Gravastar, by contrast, leaves the room unlocked, even if it takes us eons to open the door. There is a sense of continuity, of unfinished conversation. The universe does not erase its past entirely, it keeps it in quiet storage. Of course, the mathematics of Gravastars is still being explored, and they are not yet part of the mainstream astrophysical model. But their appeal lies not only in their potential to solve the paradox, but in the fact that they let two pillars of modern science share the same stage without shouting each other down. They remove the need for physics to choose between its most successful theories. You could think of it like a bridge between two cliffs. For years we have stood on one side holding general relativity, and on the other side holding quantum mechanics. The gap between them is deep, and falling into it means losing coherence in our understanding of reality. Gravastars are not the only bridge proposed. There are others, such as loop quantum gravity and string theory models, but they are one of the few that work by reshaping the landscape itself, removing the abyss by making the ground more solid. If the universe prefers such endings, then perhaps it is telling us something about itself, that it does not deal in infinite extremes but in transformations. That collapse does not mean erasure, but change. That the places where we expect finality might instead be the places where the story takes a quieter, more reflective turn. And maybe that is the lesson hidden in all of this, that the universe itself does not like hard endings. Stars die, but their material becomes the seeds of new stars. Galaxies collide, but the result is another galaxy, sometimes more vibrant than before. Even the most extreme gravitational traps might not be the cold, final prisons we once thought, but patient keepers of energy and history. In the next and final session, we will leave the details of theory behind and rest with the image of a Gravastar itself, a dark, quiet star without a horizon, holding its secrets in perfect stillness while the universe hums around it. Somewhere in the darkness between the stars there may be an object that does not roar, does not burn, does not shine. It does not collapse endlessly into nothing, and it does not erase what touches it. Instead it rests, vast, dense, and quiet, holding everything it has gathered in a perfect stillness. You could pass it without ever knowing it was there, unless you listened very carefully to the way it bends the light and the silence around it. If you could stand at a safe distance from such an object, a Gravastar, you might see nothing but darkness where the sky should be, the stars behind it swallowed by its gravity's bend. Around its edges, a faint ring of light might trace a slow circle, not from the Gravastar itself, but from the matter that still dares to fall toward it. That light would not tell you what is inside. The shell would keep its secrets. But you might feel, in the way it holds its shape, that there is something different here, something that does not end in the violence of a singularity. Inside, space could be calm in a way that seems impossible for something so heavy, so compressed. The dark energy core would push outward against the shell, not enough to tear it apart, but enough to keep it from falling in on itself. If you could float there, weightless, you might not feel trapped at all. You might feel as though the space itself wanted you to keep moving, to keep drifting. It is tempting to imagine the Gravastar's surface as a kind of memory wall, storing the history of everything it has touched. Photons that brushed it, particles that collided with it, fragments of stars, clouds of gas, each leaving a faint imprint. Over time, those imprints would form a record too complex for us to read, yet still present. It would be like an unmarked library in the middle of the night, holding every book anyone has ever left there, waiting for a reader who may never come. In this vision, the Gravastar is not an ending but a pause. Matter and energy come to it, meet the surface, and then, in their own time, some of them leave again. Transformed, slowed, but not erased. It is as if the Gravastar breathes on a timescale too slow for us to see, drawing in and letting go over millions or billions of years. From a great enough distance, it is just one more point of gravity in a universe filled with them. But in its own way, it is also a keeper of balance. It does not hoard everything forever. It does not surrender everything at once. It waits. And in that waiting, it allows the universe to flow around it without being diminished. Perhaps the most comforting thought of all is that if such objects exist, they remind us that not everything in the cosmos ends in destruction. Some things end in preservation, in patience. A Gravastar does not need to be loud to have a purpose. It simply exists, holding its place, its history, and its quiet shape, while galaxies turn and stars are born and die around it. And maybe, on some scale we cannot yet imagine, the universe itself is like this. Not a black hole swallowing all possibility, but something more like a Gravastar, where nothing is truly gone, only waiting in a form we do not yet understand. If that were true, then everything we are, everything we have been, might still be somewhere, held in a quiet place, until the time comes for it to return. You don't need to solve the equations to feel the stillness of that idea. You can just let it sit with you, like the sound of a far-off tide you cannot see. It is steady, it is patient, and it asks nothing of you but to rest in its presence. So sleep now, little star without a horizon. Sleep and keep your secrets. The universe is wide enough to wait, and the night is long enough for us to rest alongside you. The light will come again, but for now, there is only the hush of space, the quiet hum beneath all things and the gentle pull of gravity, not to destroy, but to hold.